Mba633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. This is our third segment on the topic of multiple linear regression, and here we will look at the diagnostics generated by Excel in connection with the example that we had where we're trying to predict the winning percentage of football teams using 8 independent variables, x1 through x8, which were described in the first segment. Examples of the independent variables are intercepts taken away, fumbles taken away, passing yards per game, and so forth. So in the prior video clip, the one just before this one, we had investigated what these coefficients, the estimated coefficients from the regression meant, how they were interpreted, and the estimated equation. So if you recall, in our very first discussion of multiple linear regression, we had said that one of the major differences in reviewing and understanding the diagnostics associated with multiple linear regression and simple linear regression is how one goes about testing the significance of the output, the equation that's been generated by the regression. Okay, so if you recall, there were two separate sets of tests. One was where, now since we have more than one independent variable, we look at all of the independent variables collectively. In this case we have 8, so x1 through x8. So without being picky about who is contributing how much, the question we ask is, if we take these 8 all independent variables together, do they collectively have a relationship with the dependent variable? Do they help explain the variability in the dependent variable? Now, so the hypothesis test that we're doing over here, the null hypothesis, is beta 1 equals beta 2 equals beta 3 equals beta 8 equals 0. Now, that essentially is saying that collectively, they're saying that all of the slopes are 0. Hence, collectively, this collection of 8 independent variables tells us absolutely nothing about the dependent variable. That's the null hypothesis. Okay. And the alternate hypothesis is not all slopes are 0. Note that we're not saying that each slope is different from the other. We're saying at least one's different. Okay. So if we are able to reject this null, the conclusion that we can draw is collectively, and that's a very important thing to understand, that collectively this set of 8 independent variables does in fact help explain the variability in the dependent variable. Okay, but note, we're not making any distinction among the independent variables. We're looking at them as a group, and we're not making any distinction as to who is contributing how much to the explanation. Okay, so for now, in this video clip, we are concentrating only on this test. So the null hypothesis is all slopes are 0. All slopes for the independent variables are 0. This is for the population, remember, population being the set of all games played by all these football teams, whereas our estimation is done based on data for only one season. So the alternate hypothesis here is not all slopes are 0. So let's look at the Excel output. So we will test those two hypotheses by looking at the ANOVA output over here. All right. So you remember the MS, of course, stands for mean square. MS regression. So this 0.131969 is mean square due to regression. Okay. And then if you look at the previous column, this 1.39, this was SST. This is sum of squares, the total sum of squares of the dependent variable. All right. So the regression mean square, the sum of squares for the regression, this 1.055, if you draw an analogy from what we said when we were discussing simple linear regression, this 1.055 is the variability of the predicted values of the dependent variable. This 1.39 is the variability in the actual values of the dependent variable. SSR is the variation in the predicted values. So notice that these predicted values were obtained using all 8 independent variables. So any predicted value of y, since we have 8 independent variables in this regression equation, so you can see there are 8 independent variables over here. So this sum of squares that was obtained, okay, and this mean square for the regression is obtained using all 8 independent variables together, okay. So this 0.131 is the mean square, is the variance, okay, is the variance of the predicted values, and the term and the value below it, this 0.014, is the variance of the error terms, the difference between the predicted and the actual values. Now, intuitively, what would you expect? You would expect that if the regression fit is pretty good, if the hyperplane that we fitted through these data points is fairly close to the data points, then you would expect this particular term, the first one, to be substantially larger than the other. In other words, the predicted values, the variance of the predicted value is a lot larger than the residuals, what's left over the error terms, okay? So you remember from when we did hypothesis testing, the way we go about determining if one variance is substantially larger than another, we do an F test. So this F value 9.03 is simply the ratio of the mean square due to regression divided by the mean square of the errors. Okay, it's the same thing that we had in a simple linear regression. So there's your 9.033. So what is this 9.033 is saying that we got a ratio of the sample variances, the variances of the predicted values, and the error terms is 9.033. And the next number over here, 1.53, you remember, is the p-value. How likely is it that I would get a ratio of 9.033 if in fact the null were true as an equal? So if all the betas were beta 1 through beta 8 were 0, so in fact what we are saying is if there is no relationship between the 8 independent variables collectively and the dependent variable, how likely is it that I would see this F ratio of 9.033 or higher? Okay, so this is the p-value of your standard p-value calculation for the hypothesis test. And since we are doing an F test over here, I would use the fdist function in Excel. How likely is it that I would get an F ratio of 9.033 or higher if the null were true as an equality? The degrees of freedom for the numerator is 8, and the degrees of freedom for the denominator is 23. So it's 1.5 times 10 to the minus 5. So basically, this number's got 1.5 and it's got 4 zeros in front of it, which is a very low number. You remember the usual levels of significance that we check against is 1% or 5%. All right. So this number, if I write it out, is approximately 0.1234153. That's the p-value. That's the probability. Probability of what? What this is it's saying that if the null were true as an equality, and what it's saying is if there was really no relationship between these 8 independent variables collectively and the dependent variable, then there is only a 0.000015 probability of getting an F ratio of 9.03 or higher. In other words, it's highly unlikely that this ratio would have shown up in the sample by chance if the null were true as an equality. Okay, the null were true, meaning all the slopes are 0. So the result of this ANOVA analysis of this F test, we are concluding that the 8 independent variables collectively are significant. They help explain the variability in the dependent variable, and I could go ahead and use the regression equation that I've generated over here using the 8 independent variables. Notice one important point: we are saying the 8 independent variables collectively help explain, have a relationship with y, have a statistically significant relationship with y. We are making absolutely no comment about how much any one of those 8 independent variables contribute to the explanation of y. It could very well be that one or more of the independent variables are not very useful. So the next step would be, all right, these 8 variables collectively are statistically significant. They help explain the dependent variable y. But can I get a more parsimonious description, more parsimonious relationship? And can I pinpoint one or more independent variables that are not pulling their fair share and maybe ought to be dropped from the model? Okay, so the next video clip that we are going to look at, we are going to test each and every one of the independent variables separately and see how each one is doing in terms of contributing to the explanation of the variability of the dependent variable. So the analysis that we've just done, the examination of the diagnostics, the ANOVA diagnostics, is a collective diagnostics. We have just made a pronouncement that the 8 independent variables together collectively help explain the dependent variable y. So the regression equation with 8 independent variables collectively is statistically significant. So I could, if I wanted to, go ahead and use the regression equation with all 8 independent variables. But perhaps I can do better. That's what we are about to see in the next video segment.